Hi, friends. Welcome to another episode of Beyond the Clouds Edge to Edge Transformation. In order to make any technological change, you need a whole vertical stack below that. And I'm glad I got to know Doug over the last few days. And he works on MEMS technologies and things that are necessary to make it possible to have the latest generation of computers and hardware. Doug, tell us a little bit about you so that we know exactly where you work and how your technology is making a difference.
I'm Doug Sparks. I'm the president of Micro to Nanotechnology, M2M Technologies. We're a consulting firm. We specialize in sensors, micro machines, also called MEMS, as well as semiconductors, related product design, process, wafer process, and even supply chain issues. And from a background standpoint, I've been in this field of MEMS and semiconductors throughout my whole career, which is over 30 years now. I've been in the automotive industry, consumer, industrial, aerospace, and medical.
That's exciting. And why the name M2N?
Well, it stands for micro to nanotechnology because a lot of the technology I work with may be micro, which is micro machined, could be 10, 100 microns. But then, it goes down to the nanotechnology scheme or thicknesses and realm. I did a startup company called NanoGetters, which was reliant on very thin, chemically reactive metal films used in packaging micro machines that require vacuum packaging.
Well, tell us more about MEMS. I know it's been a hot technology for a long time.
MEMS is micro electromechanical systems. In some cases, they're optical systems. Sometimes they're chemical systems. And they're kind of a derivative of semiconductors. When I first started off in the industry, we were just doing pressure sensors, which was just thinning a wafer in a certain segment of the wafer of the chip to be sensitive to pressure. So we started using that for automotive applications, industrial, medical blood pressure applications. And then as the fab tooling changed and we introduced things like plasma etching, we were actually able to make cantilevers or comb drives. And then that led into accelerometers for airbags. That was probably another big application back in the 90s. We were able to make gyroscopes. Those had aerospace applications, but they're also used in everybody's smartphones. Anytime you turn the screen on your smartphone, that's getting a signal from your accelerometers or gyroscopes to tell the system that you've moved, that you're twisting, you're turning, and it'll adjust the screen on your smartphone. And then there's navigational features that'll tell you if you're going north or south. There's e-compasses. There's also the gyroscopes that can measure those types of motions. And they're in your smartwatch, they're in your phones, they're in your automobile, safety features, comfort features, and even in the RF systems, there's filtering to get to megahertz and gigahertz frequencies. And those are micro machine structures.
I used to think MEMS are used only in the silicon space, but from what you're saying, it's used in a plethora of applications in multiple vertical markets. Can you give us a little bit about the history of MEMS, how all this came about, and how long it took?
Oh, yeah, it actually took quite a long time. The piezo-resistive effect was invented in the 1950s. And I think the first pressure sensor was a single 1-inch wafer used for industrial applications. They replaced capacitive plate pressure sensors. It's an almost a 70-year history of development. MEMS devices typically take 20 years to go from research to high volume manufacturing. It's a long progress because it's not just creating circuits, it's creating three-dimensional moving mechanical structures on a chip and then integrating those with the electronics. And then, as you can imagine, packaging a moving device is different than packaging an integrated circuit. So you've got to have a stress-free cavity type package that doesn't interfere with motion. It can't introduce particles because particles will short out capacitive structures. It will alternate the resonant frequency of a resonator like a gyroscope or a filter. So there's a lot of wafer scale packaging that goes on in the fab where you'll vacuum package in a clean room. Those kind of stacking technologies have actually led to 3D memory devices. The 3D wafer stacking began with the MEMS field, stacking up wafers to do wafer level packaging, and that's gone on and been used, spun off into other applications.
Now, nanotech seems to be like a 1000x compression of MEMS and all that. Is that true? And if so, has it changed the use cases? Has it created more use cases as we get into nanotechnologies?
Yeah, nanotechnology, we call this NEMS, nano electromechanical systems. So they're actually building resonators that are almost hair-like. In your ear, you actually have these hair filaments that sense sound. We're duplicating that. We're making very tiny piezoelectric fiber-like structures. Those can be used for audio applications, radio frequency applications. And then, of course, you can leverage everything that leading edge node semiconductors can do. You can two-dimensionally pattern things in the nano geometries. And that is slowly being adopted by the MEMS community. Typically, MEMS devices right now are in the, I would say, 100 nanometer and bigger line widths. So it's kind of a trailing edge technology. We like to think of it as a more than more technology. So it's not following Moore's law, but it's doing some strange things at these larger geometry levels that can't be done with traditional semiconductor wafer fabrication. And whether that's three-dimensional structures, alternate materials. I recently did a project for a number of years where I was 3D printing stainless steel wafers or titanium wafers for very harsh environments. So you're building up these resonators out of titanium using three-dimensional printing, laser printing. And you're instead of using silicon, because silicon's a fragile material, it's not corrosion resistant per se. And so the MEMS technology allows you to look at a whole broad spectrum of materials to select from, and then interleave that in with traditional semiconductor layers and lithography techniques.
Wow, that is exciting. Now, as you know, traditional electronics has gone up to almost the angstrom level with 3 nanometers, 2 nanometers. Does that mean that MEMS and NEMS have a long way to go and they can continue to shrink and continue to follow something like Moore's law going forward?
I think they will. There's really no limiting factor other than it's a more expensive. Obviously, the 300 millimeter, 2 nanometer wafers are extremely expensive. You know, only Apple can afford to buy them. MEMS technology is so widely dispersed, and it's more of mature node technology. But like any mature node technology, as the capital costs go down for these tools, they'll be adopted by a wider and wider spectrum of applications and fabrication techniques.
Are there specific areas where NEMS is now used in the electronics industry?
At the systems level, it's used almost everywhere. I mean, we had angular accelerometers put on hard drives 20 years ago. So we were using them in the memory application for, disk drives and things like that. Vibration sensing. And then when you look at RF signal processing, you almost have to have MEMS to get very tight filters. We call them FBAR for FBARs or SAW devices. So they're replacing the old quartz crystal oscillators that were used in radio and things like that. They're being replaced by MEMS, which are smaller and consume less power. They're fabricated on 300 millimeter or 200 millimeter wafers. So you can just mass produce them in a much more effective and cost-efficient way than you could with old quartz technology.
Now, when you look at advanced systems these days, like those that create AI solutions and very intelligent systems or robotics, storage is becoming a bigger issue, especially the latencies depend on the processor is fast, but everything else is slower. Do you think by getting into these more advanced systems, we will be able to improve it and reduce the cost, reduce the power?
It's a possibility. It's always been somewhat cost prohibitive to adopt MEMS into memory applications because the geometries are so large. So there's always been better workarounds. Now, MEMS technologies have been used for helping to cool the chips. So making microfluidic, micromachine chips that are put on top of a microprocessor that's running hot. So there was a company that I worked with out of Santa Barbara, they actually were doing micromachined titanium wafers to make microfluidic cooling systems. So they were fabricated as titanium wafers using micromachining. They were thinned down and attached to processors, and they were hooked up fluidically to have liquid fluid cooling.
You worked in a variety of companies, Doug, from the large companies, and I believe you worked in a spin-off of General Motors and things like that.
Yeah.
And you've also worked in startups, and now you've been a consultant for some time. Tell us a little bit about the genesis of your career. How did you work in these different levels? And what are the advantages or the challenges, and why you choose to be a consultant today?
I started off in high school. I read about computer chips, semiconductors. I wanted to learn how to make silicon brains, those mysterious ICs, which were almost alien technology to me as an avid sci-fi reader, high school student. So I decided to become an electrical engineer. My freshman year, all the different engineering schools came and talked to you. You went to this seminar, and the material science professor really intrigued me because that was really drilling to the core of what I wanted to learn about. So I switched to material science, where I could really deeply dive into semiconductor physics, physical chemistry, and then fill up my electives with double E classes on semiconductors. So that's what I focused on. Right out of school, I was in materials, epitaxial growth. That led me to Delco Electronics, which at that time was the biggest IC manufacturer and the biggest MEMS manufacturer in the world. So automotive electronics was the big market prior to PCs. So it was a great exposure to high volume manufacturing, to improving quality. I worked in the wafer fab with ICs, first with bipolar, then by CMOS. There was another group at our company that worked on micromachine pressure sensors and accelerometers for airbags. But a competitor, Analog Devices, captured the market with a BiCMOS integrated MEMS device. And since I was in charge of BiCMOS development, I thought I can come up with some process modules that'll do micromachining. And I was good at plasma etching, so I came up with a plasma etched BiCMOS integrated platform, and that got me into MEMS. After that moment, I was in MEMS for life. I became a MEMS designer, a MEMS process developer. I eventually was the design and development manager at Delco, which became Delphi. So that was really fun, doing high volume stuff. I had a former employee who joined a startup in Ann Arbor, Michigan. She recruited me to join them. I had been working on a resonant gyroscope project for about 8 years and got that into production. And she was working on a microfluidic resonator. She needed somebody that could take this university type startup and make it actually manufacturable. So I joined a startup as the manufacturing industry guy to try to commercialize the technology. And that's essentially what I've done for the next 20 years. Whether it's a startup or as a consultant, is to come in, particularly with smaller companies that are right out of the university, they don't really know how to harden up a manufacturing process or a design and integrate the two together or do packaging. So I kind of like to do that. So I worked in microfluidics for 7 or 8 years, launched a dozen products. Some of them were medical infusion devices, some of them were fuel cells, others were industrial, some were aerospace. As part of that team effort, I had to develop a new packaging technique for these resonators. And I had to create this material that would absorb gases, because when you wafer bond things, the surfaces desorb gases and it raises the pressure. So I developed this new material. I named it nanogetters, and I created a company and commercialized that technology. I got about 50 customers throughout all segments of industry. Eventually that was acquired by a company called Materion. So they're still making nanogetters. I'm proud to go on their webpage and see they're still doing it. A European company bought our microfluidic devices, and they're making them in Germany and Switzerland now. So they're still selling that. That's always rewarding to see something you worked on for years, a decade later, it's still out there and still working.
We keep hearing that the United States and Western Europe are losing a lot of the manufacturing expertise, and it's gone to Asia. Is it continuing to happen? And what about the strength of supply chains? What will it take to have healthy supply chains in every part of the world?
Oh, yeah, yeah. Speaking of going to Asia, one of my former designers met me in a conference in Chicago and asked me to help her start up a fab in Asia, in China. So back in 2011, I actually was helping start up a 200 millimeter MEMS fab in China with a company called Hanking Electronics. And working there over the course of almost a decade, I became very familiar and very enmeshed in the supply chain in Asia. We traveled to every town, every major facility in China. You know, we had suppliers in Korea, we had suppliers in Japan, Thailand, all over that part of the region. When the COVID pandemic hit and the supply chains were locked up, I got a lot of requests to first talk about the supply chain in China, because that's where COVID started, in Wuhan. And we actually had employees who were forbidden to go to Wuhan right when it started, and we didn't know why. But then we saw our Chinese facility shut down, our Italian design center shut down, and eventually the US locked down. So that's when supply chains became a hot topic. So I have since helped a lot of companies as a consultant work through the problems of the supply chains initially, which were COVID related, just-in-time management related issues. And now you look at geopolitical issues, things are regionalizing. And so that's a whole new spectra that everybody's becoming familiar with, that there was so much intense advanced node CMOS manufacturing in Taiwan and South Korea. And then it was growing in China. Now you're seeing these regional centers develop, whether it's friendshoring, nearshoring, whatever. That's been a really interesting topic and an interesting discussion point in consultant business for the last couple of years.
New terms every day, friendshoring, nearshoring.
Yeah.
What about the vertical integration that's happening in the automotive and other spaces?
When I was with General Motors, they were totally vertically integrated. They made all their wafers. We actually grew all our silicon crystal, made the wafers, made discretes, made ICs. They actually did germanium before they did silicon. And then we made our own MEMS devices. We did our own packaging. A lot of it was in the US. We then started sending that to Mexico and Singapore for packaging. So at that time, Singapore was a relatively undeveloped country, hungry for technology. We did the same thing with China. We did assembly in China. And it got to the point where General Motors decided they wanted to outsource everything, and they spun off their component divisions, which was the Delphi group. That was the electronics, the electrical, the oxygen sensors, the braking systems. Those were spun off. They became quite a hollowed out, outsourced entity. And then when COVID pandemic hit and the supply chain chip shortage hit, they were really in trouble. Their wafer fabs that they had in the Midwest were totally empty. They had been sold off and they couldn't get wafers and chips. So that was an interesting, ironic turn of events. And then about 2 years ago, people started talking. We actually were approached at one of my clients, which is a foundry, a wafer foundry. You know, they want to go back to vertical integration. They wouldn't mind having their own MEMS or IC research center, maybe even do low volume production internally. So it's been interesting to see the commercial and national vertical integration raise its head and being adopted, even though it's going to cause a huge rise in prices. And that's what we're seeing, you know, inflationary type pressures.
You mentioned that nanotechnologies and MEMS are used in RF applications. Does that mean they're used in 5G, 6G networks?
Oh, yeah. It'd be impossible to have them without having resonating MEMS filters for signal processing. You've got timing clocks, silicon oscillators that do the timing. There's a company called SiTimes that was the leader in MEMS timing. And you have RF switches. So you actually have micro-machined metal-to-metal switchers. So those are the three big RF devices that are MEMS natures. And without them, you couldn't do 4G or 5G or 6G is coming up.
I can clearly see that your dream of building silicon brains has come true in many different ways. But the conventional wisdom among young people or anybody is that silicon brain means learning PyTorch and TensorFlow at the software level. What career advice would you give to somebody looking at creating a career in some of the most advanced technologies?
It depends on what you like to do. If you're a coder, You want to stick with that. I've always been an experimentalist and a material scientist, so I want to work with real materials, and I want to push the limit and discover new materials and new applications for materials, or less expensive processes or ways to shrink things, and which is critical to making the AI chips or the quantum computing. There's so many interesting applications for new technology. It never ends. Quantum computing will be impossible without new materials and new processing techniques. It just goes on and on. And it was another interesting thing I've become aware of the last couple of years is you've seen nuclear fusion, the big record-breaking fusion advances they're making at Lawrence Livermore National Labs. The core piece of that is actually a micromachined diamond-coated shell. So without silicon micromachining, they couldn't have broke that record to contain that deuterium and make a tiny little target. So it's used everywhere. And I'm amazed. I keep finding new applications for it that I wasn't even aware of. Diamond is going to be big in power devices because it's a big wide gap semiconductor. Graphene's already been used in memory. That's a similar material. And diamond shells are being used in nuclear fusion. So it's crazy how all these new materials we develop in the IC fabrication research areas are finding other applications, whether it's machine tool hardness, nuclear fusion, quantum technology. It's just going everywhere.
Tell us more about quantum technologies. I mean, quantum computing has been a buzzword for more than 20 years, but every time it looks like a mirage. Having been on the materials side, do you see it coming to fruition in the near future?
Yeah, the big problem is decoherence, quantum decoherence. And so how long can you keep these states working? And so the one approach that gets the most publicity, you see all those gold, these gold meshes of wires and tubes coming down. That's to cool down the chips that Google and IBM make to like millikelvin to try to stop the ions from vibrating or the atoms from vibrating in these chips. So they're using extremely low temperature cryogenics to try to overcome the decoherence problem. There's about 20 different ways people are trying to do quantum chips. One of them that I really like is MEMS based. They're doing vacuum sealed wafer bonding with an ion vapor in it. And so they're using this ion vapor, which has electron shells that you can manipulate with magnetic fields or electrostatics or thermally, but to create these different quantum levels. But this thing has to actually be heated up to about 40 to 50 degrees C to get this vapor, this metal vapor to form. There's some really interesting, promising work being done with these micromachined. They're actually optical. I call them quantum chiplets, because you have the vapor trap in the middle, which is the micromachine part. You have a semiconductor laser on top, and you have a photonic receiver on the bottom. You're stimulating this optically. It's contained with a micromachine vapor cavity, and it has to be heated to 40 degrees C. So that has a lot of promise for room temperature applications if they can get over the decoherence issues. So in my opinion, I think the millikelvin cryogenic AI chips are more like the old ENIAC system, the computer that filled up a huge room back in the 1950s. The MEMS approach could actually be a room temperature personal quantum computer chip that could be used for personal AI. If you could do it at room temperature or just a little bit above room temperature, it could be on your watch. So that would be revolutionary.
And nuclear fusion has been a dream again for centuries, and especially after nuclear fission became possible more than 100 years ago. What's your prediction on when will nuclear fusion be commercially viable?
Yeah, it's always 50 years in the future. That's what I've heard my whole career, because I remember as a freshman in college looking at this, because I thought about material science, nuclear engineering, and it's like 50 years in the future. The interesting thing with the National Ignition Facility experiments was they got more energy out than they put into the vacuum chamber. There's 192 lasers that compress this and cause this inertial confinement. However, there was like 300 times more power needed to power those lasers up. When you think of the total system, it just had a gain of 2 or 3 when you just look at the small vacuum chamber where they imploded the nuclear fuel. So I heard one of the scientists say, to do this cost effectively to generate power, you'd have to do 900,000 ignitions a day. So about 11 or 12 a second. So you think, wow, they can't do that because they're doing one every 6 months right now. Yeah, I've actually got an article coming out next month in CMM magazine about this. So the analogy I like to draw is coal power. So 2,000 or 3,000 years ago, people were using coal in campfires. So you were throwing one chunk in with the wood and you got some more heat. That's kind of where we're at now. So to become an efficient generator of power, we obviously had to have the Industrial Revolution. So we had to have a lot of stuff in parallel. They had to learn how to not throw shovels into the steam boiler. They had to have a conveyor belt. They had to crush the coal into pellets and just feed it in nonstop. And that took 100 years or so. So you think, okay, 900,000 nuclear micromachine pellets a day is huge. We can make 900,000 ball bearings a day or 900,000 computer chips a day. I thought that was somewhat insurmountable. But then I saw a video about ASML's EUV stepper, their aligner. It's used by TSMC and Intel to make those 5 and 2 nanometer devices. To generate that 13.5 nanometer wavelength, they have to squirt in a little pellet of tin and hit it with 2 lasers to generate that wavelength. And they have to do 50,000 of those a minute or a second. So they're constantly laser ablating these tin pellets to generate the UV. And it's faster than what you have to do to generate the nuclear fusion. I think it's 100 times more frequent. I believe 50,000 a second to generate that constant EUV stream. Well, the point is, ASML has figured out how to laser ablate just a huge stream of these tin pellets. And could Lawrence Livermore National Lab figure out how to do the same thing with these deuterium tritium pellets? Maybe it's going to come faster than we think.
Now you're talking science fiction. Quantum chiplets, micro machine pellets. This is really cool stuff.
CBS 60 Minutes did a video, back in January after the December breakthrough that Lawrence Livermore had. They went to the lab and they talked about all this. They showed the pellets and they said, yeah, we shot one of these pellets and we got more energy out than we put in. The researcher said, but we'd have to do 900,000 of these a day to generate electricity. So that's where I got that number. And then on YouTube, there's something about the ASML EUV stepper, and that's where I got the 50,000 per second tin droplet laser zapping tooling that already exists. It's out there. If you can get clever people to figure out how to merge those two together, maybe in 10 years, you'll have nuclear fusion generating power. And there's a lot of nuclear fusion startups, and they're doing other plasma confinement techniques, but you just never know. If you get enough ideas out there and some venture funding, what could happen?
So, Doug, given that a lot of this technology is happening around the world, are there opportunities for people to work in MEMS and in fabs in the United States today?
The United States was a leader in MEMS. Like I said, the automotive industry, Motorola was blood pressure sensors, accelerometers, Delphi and Delco, but then they outsourced it. So Europe took the lead. So think of Bosch, ST Micro, those were the leaders. TSMC is now doing this in Asia, but there is a big push to bring that back to the US. There's new companies that are doing that. I'm actually working with a startup company called InchFab. They build small modular fabs that can be put in industrial parks. There's one actually in Silicon Valley. They're running wafers. It just started up by using small tools, small volumes of chemicals, the environmental constraints that would prevent an Intel or an IBM from building a big wafer fab now. You couldn't do that in Silicon Valley. You can put these small fabs in with small amounts of chemicals, avoid certain chemicals like chlorine that are hazardous, selectively choose your materials and your gases and your liquids. You can do that, and you can do it almost anywhere in the world. So that's kind of a revolutionary new approach to doing MEMS technology, or you don't have to do just silicon. You can have glass wafers. We can have the 3D printed metal wafers. We can have gallium nitride, silicon carbide. You can do all these novel new materials in these small modular facilities. And we've got one in Silicon Valley, one in Singapore. We've talked about putting them in the Middle East. Yeah, you can make microfabs today relatively quickly, extremely low capital expense, probably 100x from a normal fab. It would be 1,000x cheaper than a TSMC fab. smaller floor space, and you can put it in existing facilities.
So tell us more about applications of MEMS in the medical industry. I mean, all these new devices and things that go inside our skin and all that. How is it possible?
It's all started off with blood pressure sensors, which are in blood pressure cuffs. So then people started thinking, could I insert it into a catheter and put that in the heart? And sure enough, we were able to shrink the pressure sensor down to a grain of rice size and put it on the tip of a wired catheter. The next novel thing we came up with about 20 years ago was, could we embed that? Could we implant it and then leave it there? Because congestive heart failure, for example, is one case where you need to know a pressure. It varies as the heart beats, the pressure changes. It's squirting the blood around your body. When you get congestive heart failure, it starts to work less effectively. So one of the projects I worked on was making a MEMS or micro machine pressure sensor. It had to be batteryless, it had to be wireless, and it had to be surgically or catheter implanted into the heart. So that was a very interesting project because the materials had to be biocompatible. I mean, blood will dissolve gold, so you can't just gold coat things. It almost comes down to using things like titanium and Pyrex. Those are two materials that you can work with that are biocompatible and they don't dissolve in blood, which is like salt water with white blood cells attacking everything. It's a very aggressive environment. So we ended up making this Pyrex-based wireless device. It was implanted with a catheter. It had titanium catheter legs that would allow it to be embedded in the heart wall. And then once that was done, you had this wireless reader that would telepower the part, read the pressure, and you could tell the patient, okay, you're responding well to your blood pressure treatment. Or if it's not working well, they would adjust the medical treatment. So this was a totally implanted, biocompatible, FDA approved, which was really tough, implanting a device that's going to stay there, a device that was implanted in human application. Now they're doing brain implants for traumatic brain injuries. They're putting them in bladders. They're doing these things to treat diabetes. They're even trying to make artificial organs like liver, and kidney that are biocompatible materials that are engineered and implanted into people.
You mentioned something about the fact that they had to be without using an external source of energy. Where do these micro machines or nano machines get energy from to be able to be sustainable long term inside the body?
So you've got to integrate an antenna into the design. The sensor was capacitive. Essentially, it was an LC circuit. The inductor was the antenna. It was telepowered externally with an RF field. As the capacitance varied, as the blood pressure varied, that signal changed. So you didn't have to have a battery. You can monitor blood pressure changes through the capacitance change in this LC circuit. There are limits. There's FCC limits, and you can actually burn the skin. If you get too close to a radar dish, you can actually microwave yourself. So there's RF limits and there's biocompatibility.
Now you're really talking about science fiction and how.
No, this is real. This isn't science fiction.
Doug, what about all these Neuralink kind of technologies that implant stuff into your brain directly? What do you think about that?
I was at an Ann Arbor, University of Michigan spinoff, and we did biomedical stuff. So like Ken Wise, I think 20 to 30 years ago, they started making these micro machine, heavily doped silicon needles just for neural recording and neural stimulation. So they would basically have these little needles of silicon. They'd implant them into brains. They started with animal studies and things like that. They had all these issues with biocompatibility, recording the signal, cell growth over time. White blood cells want to coat these things up. So there's all these material issues, whether you switching from silicon to titanium, which is a little bit better, or other alloys. But that's where the Neuralink idea came from, was universities doing this basic research. I remember it was a really interesting DARPA program where they were implanting them into large beetles, and they could control the flight of the beetles. They had brain implants, controlling these bugs to fly, conducting spy missions with bugs. Well, that was kind of an extreme thing that DARPA always tries to push for these extreme projects. That's kind of the genesis of Neuralink. Converting that to trying to treat traumatic brain syndrome, traumatic brain injuries, or epilepsy. There's things that you can do for.
Doug, you mentioned about use of these little machines, nanoparticles, nanomachines inside the body, that it has to be biocompatible. As an engineer, how did you learn about these things? I mean, definitely it was not in our engineering curriculum per se.
Yeah, so one of the things I did after working in this for about a year, I decided to go back to school. At night school, they have classes in anatomy. You can take microbiology. I think it's like basic for nursing classes or med school. And so I took those classes in the evening, pathophysiology. I thought microbiology was just ideal because it's kind of like your naturally selected micro machine as cells, the cells in your body or the cells in bacteria, and what they do, what they sense. I felt it was essential if you want to be a biomedical engineer and do implants and you want to work on drug infusion, you've got to have that background. And I found
I'm glad, Doug, that we got a chance to talk about some of these things, and we'll have to get periodic updates from you. Yeah, I feel like a kid in a candy shop looking at all the technologies. And to anybody out there, I'm still a kid in a candy shop looking for new ideas, new technologies. None of us has a crystal ball as to where the future is going to be, but we can piece it together and at least get a holographic picture of what's going on. So please come forward. And Doug, thanks again. Half the things you told me are brand new to me, and I'm excited to learn all about it. If there are any references on these things, please send them to me so I can share them with people.
will do. Thanks so much. It's been a pleasure to talk to you.